Bismillahirrahmanirrahim. Viewers, today's our topic is potential in a rectangle. Now, potential in a rectangle is basically governed by the partial differential equation. This phenomena is governed by the PDE u double x plus u double y is equal to 0, where x lies between 0 and a and y lies between 0 and b. We label it as equation 1a. The phenomena of potential in a rectangle is governed by the partial differential equation u double x plus u double y is equal to 0 with the boundary conditions ux0 is equal to f1x equation, where x lies between 0 and a. Let we call it 1b. The other boundary condition is uxb is equal to f2x, where once again x lies between 0 and a, and let we call it 1c equation. These are two boundary conditions which are obviously non-homogeneous boundary conditions. ux0, where y is kept 0 and x varies from 0 to a, and in this case ux0 is equal to a function of x, which we assume that f1x. Similarly, for the second boundary condition, y is kept constant b, and once again x varies from 0 to a, and uxb is another function of x, which we assume to be f2x. Now we have further two boundary conditions in which x is 0, and this is, we say, homogeneous boundary condition. Here x is kept 0 constant and y varies from 0 to b. Similarly, another boundary condition where x is kept a and y once again varies from 0 to b, and these are the boundary conditions 1d, 1e. Once again I repeat, the phenomena of potential in a rectangle is governed by this partial differential equation, which I have told you in the last lecture, Laplace equation. It is the Laplace equation in 2 dimensions, and these are 4 boundary conditions. 2 of them are non-homogeneous boundary conditions and 2 of them are homogeneous boundary conditions. Now why we say potential in a rectangle? Look at diagram, x-axis and y-axis. What we are saying here, x varies from 0 to a and y varies from 0 to b, and the shape of the formed is a rectangle. Look at the boundary conditions, x varies from 0 to a, and here y varies from 0 to b. X varies from 0 to a and y varies from 0 to b, and these boundary conditions basically make the rectangle. That's why we are calling it potential equation, potential in a rectangle. Now this is basically this phenomenon is governed by these equations. Now we have to solve these equations. How can we solve these equations? First of all, we assume its solution be, let uxy be equal to x of x and y of v. Obviously this is second order partial differential equation, which I have told you that this is the Laplace equation in 2 dimensions. We can write it as partial square u over partial x square plus partial square u or partial y square is equal to 0. And when you are taking its partial derivative with respect to x and y, it assures you that u is a function of x and y. U is a function of two variables x and y. That's why you are taking its partial derivatives with respect to x and with respect to y. Obviously, u, which is a function of x, y, the solution of this equation will be of the form uxy. Now, if this is the solution, we have assumed that this solution, which is a function of x and y, we have taken it the product of two functions. One of them is function of x and the other is a function of y, in order to separate the variables. I repeat it, as we know, the solution of this differential equation will be function of x and y. I intentionally suppose that this u of xy is a function of this form. Obviously, x of x is purely function of x, y of y is purely function of y. When we take its product, this will become the function of x and y. I intentionally suppose that uxy is this form. Uxy is the form of the product of two variables functions, x and y. Why we are taking this form? This will be clear shortly. Let's suppose this is equation number 2. I think you have understand that why we are taking this u of xy in this form, because going ahead we will separate the variables. Now, if this is the solution of equation number 1a, then this must satisfy equation number 1a, be the solution of 1a, then this must satisfy equation 1a. That is, now what does it mean? Now, when you take its single derivative with respect to x, what will happen? Keep in mind, ux means you are taking partial derivative of u with respect to x, partial derivative of u with respect to x. While taking partial derivative of u with respect to x, y is kept constant. Then what will happen here? This will be x dash and y is kept constant. Y remains as it is. Similarly, when you take its double derivative, partial square u or partial x square, this will become u double x, and once again y is kept constant, and you are taking one more derivative of x, which will become x double dash, and keeping y as it is. Similarly, when you take second order partial derivative of u with respect to y, x is kept constant, and here you will have y double dash. Obviously, y double dash means second order derivative of y with respect to y. Now, we put these values u double x and u double y in this equation. In this equation, u double x mean x double dash y plus x y double dash is equal to 0. Now, you will feel why we have taken the solution of the differential equation in this form, because here we are able to separate the variables. Now, separating the variables, we have separating the variables, we have, how can you separate the variables? By dividing this equation by xy. Look at here, we have x double dash y plus x y double dash is equal to 0. When you divide by this left hand side by xy, what will happen? X double dash y over xy plus xy xy double dash over xy is equal to 0. This will become x double dash over x plus y double dash over y is equal to 0, and the variables are separated here. x double dash over x, it is independent of y, and in the second term y double dash over y, it is independent of x. Therefore variables have been separated. We have x double dash over x plus y double dash over y is equal to 0. Now we can write it as x double dash over x is equal to minus y double dash over y. Understand? Now look at here. On the left hand side, when you reach here, x double dash over x is equal to minus y double dash over y. What will happen on the left hand side if we take its partial derivative with respect to y? Means when we take it partial derivative with respect to y of left hand side, what will happen? Keep in mind, this term in this form do not have y. So when you are taking its partial derivative with respect to y, what will happen? 0. It will become 0. It will become 0. On the other hand, now if its partial derivative with respect to y is 0, obviously its partial derivative with respect to y will also be equal to 0, because this is equal to this. Now if its derivative is 0, then obviously that right hand side's derivatives are also 0, in spite of the fact that involves y. It looks like it involves y, but even then partial derivative with respect to y 0, 0 indicates that in this format it does not involve y, otherwise it could not have been 0. Similarly, when you take the right hand side's derivative with respect to x minus y double dash over y, obviously this will become 0, and if its partial derivative with respect to x is equal to 0, obviously then its partial derivative with respect to x will also be equal to 0. Means in this format both terms are constant terms. Why? When we take its partial derivative with respect to y, this becomes 0, and ultimately its partial derivative with respect to y will also become 0. And when we take its partial derivative with respect to x, that becomes 0, and ultimately partial derivative of this term with respect to x will also be equal to 0. Obviously, what it indicates? It indicates in this format both terms are independent of x and y. Means both terms are equal to some constant. Now there are three kinds of constant which we can take: 0, negative and positive. But for the periodic solution, we will take it this constant as negative constant, and we assume it as minus lambda square, where lambda is not equal to 0. I have explained that in this form both terms are independent of x and y, means both terms are equal to same constant, and we are taking here negative constant. Lambda square ensures positive, and this negative sign ensures negative constant. Now from these assumptions, we will have x double dash over x is equal to minus lambda square, and minus y double dash over y is equal to minus lambda square. From here we have x double dash is equal to lambda square x, and from here we have y minus x double dash is equal to minus lambda square x, and from here we have y double dash is equal to lambda square y. Is it clear? From here we have the second order differential equation, x double dash plus lambda square x is equal to 0, and from here we have y double dash minus lambda square y is equal to 0. Now look this equation, this is the second order ordinary differential equation, which can be written as d square plus lambda square x is equal to 0, and its auxiliary equation will be d square plus lambda square is equal to 0. This will give you d square is equal to minus lambda square, and from here you will have d is equal to plus minus iota lambda, complex roots. And whenever you get the complex roots, the solution will be x of x will be a dash cos lambda x plus b dash sin lambda x. Understand how this becomes? When you solve the second order differential equation, y double dash minus or 4 y is equal to 0, its auxiliary equation is d square plus 4 is equal to 0, and d is equal to plus minus 2 iota. And what will be its solution? A cos 2x plus b sin 2x. Exactly, this was the second order ordinary differential equation. Its auxiliary equation gives you the roots d is equal to plus minus iota lambda, and its solution will be x, some constant a which I use here a dash, and the other constant b dash. Now what will happen here? Obviously this will become d square plus lambda square y is equal to 0, or d square, its auxiliary equation is d square minus lambda square is equal to 0, and this will give you d is equal to plus minus lambda. This gives you the positive, this gives you the real roots, and when you get the real roots, we can write two kinds of the solution. How can we write two kinds of the solution? Look at here. If we have y double dash minus 4y is equal to 0, its auxiliary equation d square minus 4 is equal to 0, d is equal to plus minus 2. Now its solution will be, either you can write it as a e raised to power minus 2x, where, and other b e raised to power 2x, and its alternative form is, you can write it as a cos hyperbolic 2x plus b sin hyperbolic 2x. You have already studied it. If the roots are imaginary, then solution is of this form. But I am doubt that you have studied this form of the solution or not. I think you haven't studied this form. When the roots are real, then this is the another form of the solution in the hyperbolic form. Obviously these roots are the real roots, therefore y will be, let us suppose, c dash cos hyperbolic lambda y plus d dash sin hyperbolic lambda y. Now look at the solution. You have supposed that uxy is a solution of original differential equation, partial differential equation, and at this stage you have got the product functions x of x and y of y. But one thing which we have to find, the four constants. Now how can we proceed further? Putting these values in equation number 2, putting these values into, we will have uxy is equal to x of x a dash cos lambda x plus b dash sin lambda x into c dash cos hyperbolic lambda y plus d dash, here we should write sin hyperbolic lambda y, and this is the basically solution in which we have to find the four constants a dash, b dash, c dash and d dash. Let me label it equation number 3, this is 2, and let me label it equation number 3. Now as you know, in order to find the values of constant, we have to use the boundary conditions. Now first of all, you use this boundary condition, ux0 is equal to f1x. Now how can you use this? You write here ux0 is equal to f1x, means when you write y0, this will become ux0 and this will become f1x, and on the right hand side when you put y is equal to 0, I think you first of all use the homogeneous boundary conditions. First of all use the homogeneous boundary conditions, and the above two boundary conditions will be used later on. Put x is equal to 0. Put x is equal to 0 mean u0 y is equal to 0. These two are the homogeneous boundary conditions. First use these two boundary conditions, and later on we will use the non-homogeneous boundary conditions. When you put x is equal to 0, what will happen here? This implies 0 is equal to a dash into c dash cos hyperbolic lambda y plus d dash sine hyperbolic lambda y. Am I right? You have put here x is equal to 0. This will become, when you put x is equal to 0, then you have to put here x is equal to 0. Cos 0 will become 1 and sine 0 will become 0, and you will have only a dash here, and this term will remain as it is because this term does not involve x. Now either a dash is equal to 0 or this term is equal to 0. Obviously if you assume that this term is equal to 0, then your solution will become 0. If this is 0, then the solution will be 0. So we assume that this is not equal to 0 because this is not equal to 0, otherwise you get the trivial solution. You will get the 0 solution. That's why from here you will get a dash is equal to 0, and you are writing the argument since c dash cos hyperbolic lambda y plus d dash sine hyperbolic lambda y is not equal to 0. Now out of 4 constants, we have found the value of the one constant a dash. Now putting this value in equation number 3, we will have, if you put a dash is equal to 0, then obviously equation number 3 becomes uxy is equal to b dash sine lambda x into c dash cos hyperbolic lambda y plus d dash sine hyperbolic lambda y. Now out of 4 arbitrary constants, the value of the one constant is found to be 0, and look at here, these 3 constants will become 2 constants. How? uxy is equal to sine lambda x into b dash c dash cos hyperbolic lambda y plus b dash d dash sine hyperbolic lambda y, and this b dash will be absorbed in these 2 constants. When we multiply b dash c dash, this will become another constant, and when we multiply b dash into d dash, this will become another constant. Then reducing the number of constants, we see here 3 constants, but in fact these are not 3 constants. These become 2 constants, and final solution becomes here uxy is equal to sine lambda x, and we label it a b dash c dash as a constant a cos hyperbolic lambda y, and we label this constant b dash d dash as constant b sine hyperbolic lambda y, and this is the required solution, in which once again we have to find the values of constants a and b. Now, so far we have applied only this boundary condition. When you apply another boundary condition, what will happen here? You put here x is equal to a and remain y as it is. UAY is equal to 0. This becomes 0, means when you put x is equal to a, y remain as it is, this becomes 0. And here put x is equal to a in place of x. This becomes sine lambda a, and this term will remain as it is, a cos hyperbolic lambda y plus b sine hyperbolic lambda y. Once again, this term will not be equal to 0, otherwise solution will become 0. Therefore, you will have sine lambda a is equal to 0, and reason is that a cos hyperbolic lambda y plus b sine hyperbolic lambda y is not equal to 0. Otherwise, solution becomes 0, because if you see this is the solution, and if in this solution this term is 0, obviously solution becomes 0. This should be non-zero. And what we get from here? We get from here lambda a is equal to sine inverse 0, and this will give you lambda a is equal to n pi, where n is equal to 1, 2, 3 and so on. And now you see here the lambda constant which you have introduced here have infinite values. Lambda a is equal to n pi, n is equal to 1, n is equal to 2, n is equal to 3. From here we will get infinite values, and we label these infinite values by lambda n pi over a, and these are known as eigenvalues, where n is equal to 1, 2, 3 and so on. Understand? Now let me complete it by saying that if eigenvalues are infinite, then corresponding to these eigenvalues we will have infinite constants a and b. Infinite constants a and b, because when you put one value of lambda, first value of lambda, you will get the solution, and these constants will be a1 b1. When you put lambda 1, these constants will be a1 b1, and this solution will be u1. Now corresponding to corresponding to each eigenvalue you will have a solution, and by the principle of superposition their linear combination will also be the solution. Thus the complete solution is, which we say uxy is equal to sigma n varies from 1 to infinity sine lambda n x into an cos hyperbolic lambda ny plus b. Let me write here now the complete solution becomes uxy, which is basically the summation of the solutions. Sigma n varies from 1 to infinity sine lambda nx into an cos hyperbolic lambda nx, an cos hyperbolic lambda ny plus bn sine hyperbolic lambda ny. This is basically complete solution, and we label it as equation number 5. Now our last problem is to solve the to find the values of an and bn. Now how can we find the values of an and bn? Remember, there are two boundary conditions we yet not used. What were those boundary conditions? Ux0 is equal to f1x. These are the boundary conditions. I think I have rubbed those boundary conditions. Ux0 is equal to f1x, and the other boundary condition ub. What was the second boundary condition? The first boundary condition is ux0 f1x, and the other ux b is equal to f2x. Okay. Now we use the first boundary condition, ux0 is equal to f1x. Now when we put y is equal to 0, this will become ux0 and this will become f1x. On the right hand side, we have to put y is equal to 0. Sigma n varies from 1 to infinity sine lambda nx. When you put here y is equal to 0, cos hyperbolic y is equal to 1. This becomes an, and sine hyperbolic 0 is equal to 0. When you put y is equal to 0, sine hyperbolic 0 is equal to 0, this will become 0. Okay. In order to get the value of a n, what we have to do? We have to multiply this function f1x by sine lambda mx, and we have to integrate it from 0 to a, because we are integrating with respect to x, and x change from 0 to a. And now why we are multiplying this f1x with sine lambda mx and integrating from 0 to a dx? The answer will come shortly, and you have to do on both sides. You have to operate this, you have to do this operation on the both sides. On the left hand side you have multiplied with this, and on the right hand side you will also integrate from 0 to a. Sigma n varies from 1 to infinity sine lambda nx sine lambda mx dx, and here we have a n. Now what will happen here? This will become, you can take sigma out the integral. Sigma n varies from 1 to infinity a n integral 0 to a sine lambda mx sine lambda nx dx. Now how can you integrate this? You use the trigonometric formula from product to difference or sum. In order to make this formula, we have to multiply it by minus 2. Therefore we are dividing by minus 2. Sigma n varies from 1 to infinity a n 0 to a minus 2 sine lambda mx sine lambda nx dx, and this will become minus 1 by 2. Sigma n varies from 1 to infinity a n 0 to a. This will become cos lambda mx plus lambda nx minus cos lambda mx minus lambda nx dx. This will become minus 1 by 2. Sigma n varies from 1 to infinity a n integral 0 to a. We can write it as cos lambda m plus lambda n x minus cos lambda m minus lambda n x dx. Clear? Now look at the eigenvalues. If lambda n is equal to n pi over a, lambda m will be m pi over a. This will become minus 1 by 2. Sigma n varies from 1 to infinity a n integral 0 to a cos m pi over a plus n pi over a x minus cos m pi over a minus n pi over a x dx. Once again we further simplify it. This becomes minus 1 by 2 sigma n varies from 1 to infinity a n integral 0 to a cos m plus n pi over pi x over a minus cos m minus n cos m minus n pi over a x. dx. Now look at this format. When you integrate it, what will happen? This becomes sin m plus n pi x over a and m plus n pi over a dividing by the derivative angle. And when you apply the limits 0 to a, when you apply upper limit, this will become sin m plus n pi a over a divided by m plus n into pi over a. And when you apply lower limit, this will become 0. Why? When you apply upper limit in place of x, this you will get this answer. When you apply x is equal to 0, sin 0 is equal to 0. This becomes 0. Now once again, a will be cancelled out and you will have sin m plus n pi m plus n pi over a. Now look at here, sin m plus n pi, this is once again integral multiple of pi, and integral multiple of pi is always equal to 0. So therefore this will also become 0. It will happen with all these terms, and it's very disappointing that its answer is 0. This constant is 0. No. Look at here, n varies from 1 to infinity. When n varies from 1 to infinity, somewhere it get n is equal to m. When you say n 1, 2, 3 up to infinity, obviously somewhere it will become m. At that stage, we will have non-zero answer. Is it clear? Otherwise, these integrals will be equal to 0. Therefore, we will now eliminate the summation, and we will use here am integral 0 to a cos m plus m pi over ax minus cos m minus m pi over a x dx. That's why when you have cos m minus m, this will become cos 0, this will become 1, and the answer, non-zero answer, will become from this term only. This will become minus 1 by 2 am and now we are integrating it. Its integration will be sine 2m pi x over a divided by 2m pi over a, and this will obviously become, if we write one other step, one extra step, this will become cos 2m pi over ax, and this will become minus 1 dx. This I am writing the extra step. 2m pi over a and minus m cos 0 gives you 1, and its integration will be x, and obviously we have to apply the limits as well, 0 to a. Integration of cos 2m pi over ax is equal to sine 2m pi x over a divided by 2m pi over a, and integration of 1 is equal to x. Now applying the limits 1 by 2 am, when we apply the upper limit, you will have sine 2m pi over 2m pi over a minus a, and obviously for the lower limit this will become 0 and this will also become 0, and this will obviously be equal to 0. 2m pi sine 2m pi will also equal to 0. 2m pi m plus m 2m, this one, when you integrate it, you have to divide by the derivative of the angle. When you integrate cos 2x, its integration will be sine 2x over 2. Understand? Obviously 2m pi over a is the derivative of this. This is the angle. Sine's angle is 2m pi x over a. Its derivative with respect to x will be 2m pi over a, and obviously you have to divide it by its derivative as well. Now what will happen here? Minus 1 by 2, 0 minus a, and this becomes 1 by 2, rather a by 2 am, and from here the value of constant am is, look at here, 0 to a f1x sine lambda mx. This was equal to what? A by 2m, a by 2 am. From here am is equal to 2 over a integral 0 to a f1x sine lambda mx dx. We have to find the value of an, and it is value of am. What can we do here? Just replace m by n. Okay, this will become an is equal to 2 over a 0 to a f1x sine lambda n x dx. This is the value of constant an. Now what we have to do finally? We have to find the value of the constant bn, and for that purpose we have another boundary condition. Look at the solution. uxy is equal to sigma n varies from 1 to infinity sine lambda n x an cos hyperbolic lambda n x lambda n y bn sine hyperbolic lambda n y. Here we have to find the values of constants an and bn. We have found the value of an, and once again we have to find the value of bn as well, and for that purpose we have to use the other boundary condition, other non-homogeneous boundary condition. Next we find the value of constant bn using second non-homogeneous boundary condition. The second non-homogeneous boundary condition is written here, which was labeled to be equation 1c, uxb is equal to f2x. Now using this second non-homogeneous boundary condition, we are going to find the constant bn as we found the constant an using the first non-homogeneous boundary condition. Now look at the procedure. Obviously, this is the solution uxy. Here we will put y is equal to b. Then what happens? Uxb is equal to sigma n varies from 1 to infinity sine lambda n x a n cos hyperbolic lambda n b plus b n sine hyperbolic lambda n b. What I am going here? I am just putting y is equal to b on both sides. Here putting y is equal to b, we will get uxb, and here sine lambda nx will remain as it is, and here y is replaced by b. Once again y is replaced by b. Now as you know, this uxb is equal to f2x. Therefore we put here f2x, which is sigma n varies from 1 to infinity sine lambda nx into a n cos hyperbolic lambda n b plus b n sine hyperbolic lambda n b. The procedure is same as we did to find the value of a n. What will we do here? We will multiply both sides by sine lambda mx and integrate from 0 to a, as we did in finding the value of constant a n. Now we are going to repeat those steps. Integrate from 0 to a, multiplying f2x with sine lambda mx, means first of all multiply this function f2x by sine lambda mx and then integrate from 0 to a with respect to x. Same operation will be done on the right hand side. 0 to a, integral 0 to a sine lambda nx into a n cos hyperbolic lambda n b plus b n sine hyperbolic lambda n b into sine lambda mx dx. Now as you are integrating it with respect to x, y at this term is constant because this doesn't involve x or y. Therefore we can write it as, and where the sigma n varies from 1 to infinity. Obviously you have to write sigma as well. Summation 0 to a, sigma n varies from 1 to infinity sine lambda nx. While we are integrating this factor by multiplying with sine lambda mx and integrating from 0 to a, as we read on the left hand side. Now we can write it as sigma n varies from 1 to infinity, and this term can be taken outside the integral, a n cos hyperbolic lambda n b plus b n sine hyperbolic lambda n b, and then we place here integral 0 to a sine lambda mx sine lambda nx sine lambda nx dx. And once again we are going to repeat the steps as we did in finding value of a n. Now how can we repeat? Obviously we have to multiply, we have to convert this product to difference formula. For that purpose, as we did in finding a n, divide and multiply by -2, we will have sigma n varies from 1 to infinity a n cos hyperbolic lambda n b plus b n sine hyperbolic lambda n b 0 to a, integral 0 to a -2 sine lambda mx sine lambda nx dx. and this becomes minus 1 by 2 sigma n varies from 1 to infinity a n cos hyperbolic lambda n b plus b n sin hyperbolic, here we should write sin hyperbolic lambda n, sin hyperbolic lambda n, b n sin hyperbolic lambda n b, and this integral will become 0 to a cos lambda mx plus lambda nx minus cos lambda mx minus lambda nx dx. Minus 1 by 2 sigma n varies from 1 to infinity a n cos hyperbolic lambda n b plus b n sin hyperbolic lambda n b integral 0 to a, this will become cos lambda m plus lambda n x minus cos lambda m minus lambda n x dx. And as you know, lambda n was equal to n pi over a, so lambda m will be equal to m pi over a. Now putting these values in this expression, we will have minus 1 by 2 sigma n varies from 1 to infinity a n cos hyperbolic lambda n b plus b n sin hyperbolic lambda n b. This integral will be 0 to a cos, I will put here m pi over a plus n pi over a and take pi over a common. Then this will be m plus n pi over pi x over a. Similarly here cos m minus n pi x over a dx. As I earlier told you that when we integrate this, this will become sin m plus n pi x over a, and when we apply upper and lower limits, this will give you answer 0. Similarly, from where? From here, this will give you sin, and applying upper and lower limits, answer will be equal to 0. There is only one value for which we get non-zero answer. And what is that? As I earlier told you that when you change the values from when you change the values of n from 1 to infinity, or while going the values of n from 1 to infinity, we get one value equal to m. At that value, we will get non-zero solution, non-zero value of the integral. Because I have told you earlier in finding the constant a n, therefore I proceed further. Minus 1 by 2 sigma n varies from 1 to infinity a n cos hyperbolic lambda n b plus b n sin hyperbolic lambda n b. Now this summation will be finished, and we will take only that value of n which is equal to m. Therefore, this will become minus 1 by 2 a m cos hyperbolic lambda m b plus b m sin hyperbolic lambda m b, as we did in the finding the value of constant a n. This summation will be removed, and on the inner side of the integral we have cos m plus m pi over ax minus cos m minus m pi x over a dx. Why this summation is removed here from here? While going the values of n from 1 to infinity, the only value of m when n is equal to m, that will give you the non-zero integrals answer. That's why all the remaining terms will be 0. And we will have here minus 1 by 2 am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb I need this value, therefore I am not omitting this value, and this can be written here minus 1 by 2 am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb into integral 0 to a cos 2m pi over a x minus 1 dx. Now how this becomes minus 1? Because cos m minus m cos 0, this will give you 1. Only non-zero value will be, this will give you the non-zero value of the integral. Now integrating, first of all, minus 1 by 2 am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb, and when we integrate this, this will become sin 2m pi over a x divided by derivative of the angle, which is 2m pi over a, and minus 1's integration is x, and obviously you have to apply the limits as well, limits of integration. Once again I repeat, the integration of cos is sine, and you have to divide by the derivative of the angle, and then 1's integration is x. Now we have to apply the limits, upper limit minus lower limit. Minus 1 by 2 am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb, and when we apply the upper limit here, what happens? Sin 2m pi a over a divided by 2m pi over a minus sin 0 and minus a minus 0. I think you understand how we applied the limits. When you apply the upper limit in place of x, you replace x by a and minus sin 0 divided by this thing, and upper limit minus lower limit. Now this will, a will be cancelled out with this, and when integral multiple of pi appears in the angle of sine, the answer is 0. Sin 2m pi is 0 and sin 0 is 0. What will happen here? Minus 1 by 2 am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb, and this will be 0 minus a. Obviously this minus will be cancelled with this out minus. This will give you a over 2 into am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb, and this was equal to what? This was equal to integral 0 to a f2x sin lambda mx dx. That's why we are now writing it as keeping 2 over a on the right hand side, we will have am cos hyperbolic lambda mb plus bm sin hyperbolic lambda mb is equal to what? 2 over a integral 0 to a f2x sin lambda mx dx. Hopefully you understand, because this expression is equal to this one. Therefore, taking 2 over a on the right hand side, this will give you a over 2 on the right hand side, this will become 2 over a integral, and you will have the this term. Now don't forget, we are finding constant bn. Now how can we find constant bn? We can write it as bm sin hyperbolic lambda mb is equal to 2 over a integral 0 to a f2x sin lambda mx dx and minus this one, this term am cos hyperbolic lambda mb. Now we have to find the value of bn. Just replace m by n and take this one on the right hand side and use the value of an, which I have written here. Okay, first of all, you can replace m by n. When you replace m by n and you divide this, you take this term on the right hand side, you will have bn sin, I think we after you understand here, we have found this relation and we have to find the value of bn. Therefore, we are replacing this m by n on the both sides. Due to the shortage of space, I am confining here. This is bn sin hyperbolic lambda nb integral 0 to a f2x sin lambda nx dx minus an cos hyperbolic lambda nb. I think you understand. Here we get the value of bm and we are going to replace m by n in order to get the value of bn. Now look at the steps, because we have less space, therefore please try to understand all the steps. bn will be equal to 2 over a, and when this this goes on the right hand side, this will be 1 over sin hyperbolic lambda n b. 1 over sin hyperbolic will be equal to cosecant hyperbolic. Therefore, I am writing here cosecant hyperbolic lambda n b integral 0 to a f2 x sin lambda nx dx minus, don't forget the value of an, and don't forget you are taking this on the right hand side. When this goes on the right hand side, this will become cos hyperbolic lambda nb over sin hyperbolic lambda nb. This will become cot hyperbolic lambda nb, cos over sin. Therefore, I am writing here cot hyperbolic lambda nb, and obviously this becomes, due to the division by sin hyperbolic lambda nb, this becomes cot hyperbolic lambda nb, and obviously we have to place here constant an as well. And now we are not placing the constant an here, we are placing the value of the constant an here. What is that? that is 2 over a integral of this thing. Once again I have to rewrite due to the space constraint. This becomes minus 2 over a cot hyperbolic lambda n b integral 0 to a f1x sine lambda nx sine lambda nx dx. Now once again I repeat for you. Look the step. 2 over a remains as it is. When you take this sine hyperbolic lambda n b on the right hand side, this will be 1 over sine hyperbolic lambda n b. That becomes cosecant hyperbolic lambda n b. And integral 0 to a f2x sine lambda nx dx remains as it is. Now minus an, the value of an is 2 over a integral 0 to a f1x sine lambda nx dx. And obviously when you take this on the right hand side, this will become cos hyperbolic lambda n b divided by sine hyperbolic lambda n b. That becomes cot hyperbolic lambda n b. Now this gives you the complete solution of the potential equation in the rectangle, or we also say that Laplace equation in the rectangle or potential in the rectangle. Its solution is uxy sigma n varies from 1 to infinity sine lambda nx an cos hyperbolic lambda ny plus bn sine hyperbolic lambda ny, where an and bn are calculated here. This is an and this is bn. Hopefully you understand the complete steps which I tried my best to write here. I expect that you can rewrite the problem and you can solve it yourself. Thank you very much.